Sathyabama Institute of Science and Technology.
Hello everyone, this is Dr. T. Krithiga, Associate Professor, Department of Chemistry, Sathyabama Institute of Science and Technology, deemed to be university. In this video, we are going to see topicity in stereochemistry. The content of this video will cover prochirality, homomorphic ligands, topicity in ligands, and criteria for topicity. So first, before going into what is topicity, first we will see what is prochirality. So an achiral molecule which is containing a prochiral center will have two ligands identical, so that this is not a stereo center. Now, when we replace one of that hydrogen by another ligand, then this carbon will become a chiral center or a stereogenic center. So, prochiral molecules are those which are achiral and can be converted into chiral molecules by a single step by the replacement of one of the identical group by a different ligand. So as I told you, the identical groups that is present on the molecule, prochiral molecule, are called as homomorphic groups. So homomorphic groups are present to a prochiral center, are indistinguishable in isolation, but they are distinguishable when they are part of the molecule. So these molecules are homomorphic groups, should have same constitution. So in this compound, the two hydrogens are identical and they are called as homomorphic atoms or homomorphic groups. Similarly, the bromine atoms that is present here are also homomorphic groups. And in this compound, we are having two hydrogen atoms which is represented as HA and HB, but they are identical. So this compound has a prochiral center. So as I told you, when we isolate the two hydrogens, these two hydrogens are identical and are superimposable. Therefore, they are called as homomorphic hydrogens. Similar to that, the two bromine atoms are also homomorphic in nature. So now, what is topicity of a ligand? So as I told you, when we take a homomorphic groups, the relationship between these homomorphic ligands will be called as topicity. So this relationship can be homotopic or can be heterotopic based on whether the homomorphic groups are equivalent or not equivalent. So when it is equivalent, when the two homomorphic ligands are equivalent, they are called as homotopic, and when the two homomorphic ligands are not equivalent, then they will be called as heterotopic ligands. So now, how we will find out the topicity? So this topicity can be determined by two criteria. One we call it as symmetry criteria, the other one we call it as substitution addition criteria. So to determine the topicity relationship of homomorphic ligands, we can use either one of this criteria and find out what is the topicity of the ligands. So what is a homotopic ligand? So if you see homo, that is called as same, topo means place. So they have identical place in the molecule. So their constitution is same. Now the two ligands that are homomorphic in nature, that are identical, but if you replace one atom with another ligand, then it will give rise to the identical molecule similar to the original molecule. Then we will call those two ligands as homotopic ligands. So how we can find out whether that is a homotopic ligand or not? So as I told you, there are two criteria that can be used. So first we will see what is symmetry criteria. So symmetry elements, whether axis of rotation, CN axis of rotation is present in the molecule will be determined. Okay. So two homomorphic ligands are homotopic in nature if they can interchange their places by rotation around CN axis. So this principal axis can be C2 axis, C3 axis, etc. So I have taken two axes. One is C2 axis. So if you see this molecule, it is having a C2 axis of rotation. So if the molecule is rotated along 180-degree rotation, then the HA and HB, these two are homomorphic in nature because this is a prochiral center. So these two hydrogens on rotation will interchange the places, but we get two identical molecules here. Therefore, the HA and HB are homotopic ligands. Now if you see the ammonia, this molecule is having a C3 axis of rotation. So here it contains three homomorphic ligands, H1, H2 and H3. On 120-degree rotation, we will result in identical molecules. So, this will appear in two terms. So, therefore, the three structures are identical molecules. Therefore, H1, H2, H3 are homotopic ligands. So, the second method to determine the homotopic ligands is substitution addition criteria. So, in this method, the molecule will be having two homomorphic ligands. So, one homomorphic ligand will be substituted by a different ligand. Similarly, the other homomorphic ligand will be substituted by another different ligand. Then we will compare the two structures and find out whether the two homomorphic ligands are homotopic or not. What are heterotopic ligands? So, heterotopic ligands, hetero means different, topo means place. So, they will have a different positions in the molecule. So, the two ligands that are identical but individual replacement of one identical ligand by another ligand give rise to structurally different, that is isomeric structure, then they are called as heterotopic ligands. So, to find out the heterotopic ligands, we are using the substitution addition criteria. So, in this, heterotopic ligands are of two types again. What we have is enantiotopic ligands and diastereotopic ligands. So, when it is an enantiotopic ligand, the two ligands that are identical but individual replacement of one identical ligand by another ligand will give rise to two enantiomers. Then the homomorphic groups or the homotopic or the two homomorphic groups will be called as enantiotopic ligands. So, if I take this compound again, this is a prochiral center which has HA and HB. Now, I am replacing HA and HB by Br. So, I am resulting in two structures. The stereochemistry tells that the first molecule is having an S configuration and the second molecule is having an R configuration. So, they are mirror images. Therefore, they are enantiomers. Okay. So, since the replacement of the ligands by different ligands is resulting in enantiomers, these HA and HB are heterotopic and they are enantiotopic in nature. Now, when you have two stereogenic center, then I am taking an example. This is having HA and HB as the homomorphic groups. Now, I am replacing HA and HB by X. So, I am resulting in two structures here, which is having X replaced by HA replaced by X and HB replaced by X. So, these two structures I have. The first structure I am rotating to 180 degrees in plane rotation. Therefore, I am resulting in a structure. Now, if I compare these two structures, they are mirror images. Therefore, they are enantiomers. So, the HA and HB ligands are enantiotopic in nature. If you see the diastereotopic ligands, the two ligands that are identical but individual replacement of one ligand by another ligand gives rise to two diastereomers. Then they are called as diastereotopic ligands. Okay. So, I have taken this example where I have HA and HB like this. They are homomorphic in nature now, and I am replacing HA by X. I result in this structure. So, HA is replaced by X here. Similarly, HB is replaced by X. So, I am getting two structures. Now, I am rotating the first molecule to 180 degree rotation. So, when I am doing at in plane rotation, I am resulting in this structure. But if I compare this structure with this structure, they are not mirror images, but they are stereoisomers. Therefore, they are called as diastereomers. Therefore, HA and HB homomorphic ligands are called as diastereotopic ligands. Thank you. We will see in the next video.